So let's go to number 2. Which of the following is true for a system whose equilibrium constant is relatively small? We have a small equilibrium constant, and we're using this generic reactants and products. Then we're going to have the products up here with the coefficient powers, and the reactants down here, their coefficient powers. If the equilibrium constant is very small, that means the numerator is small and the denominator is big relative to one another. That means that the reactants are going to be at equilibrium, are going to be relatively high concentration. Products are low concentration. So the let's see, equilibrium lies to the left. Yes, we have mostly reactants still in that environment. And conversely, if we have a large K, that means that the equilibrium as written is shifted far to the right. And that as written is not parenthetical, it's essential. If we wrote it differently, then the K would be different. If we wrote it backwards, obviously the K would be the inverse, according to our rules. Okay, for this equilibrium system, number 3, let's see, you've got carbon dioxide and hydrogen. Is in equilibrium with carbon monoxide and water. Okay, and we're given the enthalpy 42 kilojoules per mole. Since each of the balanced equation coefficients is 1, then kilojoules per mole could be any one of them. Excuse me. The K equals 1.6 at 1260 K. So K equals 1.6 at, that's extremely high temperature. And what else are we given? The amounts at the beginning in a 1 liter container are 0.15 moles each. And that's per liter. So there we have molarity is essentially given to us. And this is the same for each one. This is the starting conditions. Okay. Let's see, that's everything we're given. So as the system came to equilibrium, we look at the answers. The answers say something about temperature and something about the shift. So the temperature would decrease and the mass of something. It looks like it's focused on carbon dioxide, would either increase or decrease. Okay, first thing we know is this is an endothermic reaction. So where would the heat turn be? This side. No, that side, excuse me. This side. Let's make a little room. Put the heat term over here. Okay. Excuse me. How are we gonna tell which way the equilibrium shifts? Because we've got a fixed amount for each one. We have to calculate the Q. So the Q is going to be derived from the K expression. And we're going to have carbon monoxide, non-equilibrium, water, and all these terms are valid. I mean, they're part of the expression because they're gases. Okay, we don't leave any of them out. Then CO2 and hydrogen. Now, let me be sure I got that one right. Yeah, coefficients are 1 each. Okay, so really, 1.5 molar, that would be squared. That would be squared because they're the same for each one. And that's equal to 1. Okay, so if Q is less than K, what does that mean? If the Q is less than K, that means we have not enough product and too much reactant. That makes it a smaller value than K. If this is larger than it should be, and this is smaller than it should be. So it would shift toward the right, toward carbon monoxide. It would use up CO2. So our choices are for decreasing CO2 are B and E. So it's either B or E based on that argument. Now, address the temperature. What would the temperature do if we shifted this direction? It would use up some of the energy, some of the heat. So the temperature should decrease, right? So temperature would decrease, and that means B is our answer. Temperature decreases, CO2 would also decrease. Okay. All right. So if I were sneaky and I gave you different values in here and made this one say 1 point or 2.0, I could go the other direction, wouldn't it? Yep. Let's see, 4. Addition of chemical B to an equilibrium mixture of the above will what? Okay, so looks like 4 and 6, actually 4, 5, and 6 are based upon this equation. 2A, 2B, and C. 2A decomposes. 2B and 1C. They're all gases. Okay. And at any given temperature, which is not important for the questions being asked, the K is 1.6 times 10 to the 4th. Okay. That means at this temperature, the equilibrium favors mostly product. Huge amount. Reactants almost completely disappear. So what would happen at equilibrium if we add, maybe we ought to write the expression. Let's just be complete. And let's see. There we go. So if we add B at equilibrium, what should happen? If we add B, we should get a shift back this way, which would increase the amount of A and decrease the amount of C. Cause A to increase. Yeah. So number 4 would be A. Let's see, we'll skip down to 6. Using the same. Oh. 5 actually looks interesting. I know I don't have it highlighted, but let's do it anyway. At a higher temperature, K equals 1.8 times 10 to the minus 5th. K equals 1.5. 1.5? 1.8 times 10 to the minus 5th. So what's happened here? This is at a higher temperature than this one. So what we're saying is, if we increase the temperature, what have we actually done to the equilibrium? We've shifted it back this way, which means it's an exothermic reaction. We increase the temperature, then we shift it back this way, and it makes this, the K value shift very small, which means very little product. Okay, that in mind, if we put the mixture in an ice bath, lowering the temperature, what should happen at equilibrium now? Put it in an ice bath, we're reducing the temperature, we're removing this term, and we're shifting it back to the right. So that should cause B to increase and C to increase. B would be the best answer for that. Okay, now back to 6. 6. We're going to change the pressure, raise the pressure by lowering the volume. Okay. Raise P, and we do that by lowering volume. Okay. For the answer to this one, we compare the coefficients. On this side, we have 2 moles total gas. On this side, we have 3 moles total gas. So if we raise the pressure by lowering the volume, then we favor the side that produces the fewest moles, because that relieves some of the stress. So it should shift to the left. Increase A. Yeah. So that would be A. All right. Let's see. How about this one, number 8? This is based upon the complex ion hexahydrate cobalt 2 plus. We'll deal with complex ions in detail. Let's see, in this course. Yeah, later on. Okay. And this is plus 4 chlorides is in equilibrium with this complex ion. Minus. Yep. Plus the 6 waters. Okay. This is pink. This is blue. So if we have a predominance of this, of the products, well, blue solution, if we have pink solution, we know that it's predominant reactants. When cobalt 2 chloride is added to pure water, cobalt 2 plus ions hydrate. Okay, yeah, and produce this. We just add the cobalt to that solution. The hydrated form then reacts with chloride ions to set up the equilibrium shown here. Which statement below describes the change of the system will undergo if hydrochloric acid is added? If we add hydrochloric acid, and I don't see any term in this equation that would address the increase in hydrogen ions. So we're basically looking at increasing chloride ions. I suspect, just my opinion, that this system is pH dependent, right? So there is an effect here, but we're just not given that in this description, right? So we have to limit our discussion to what we know here, and that's the chlorides. So if we add chlorides, then we should shift toward the blue. Okay, yes, it would become more blue. That's true. But we also have two of these as an option, so let's look at the other. Well, it can't be blue and pink at the same time. So the C and D, the equilibrium will shift to the right, yes. Shift to the right, which would be C. So actually two of them are correct. All right. Let's see. Consider the following equilibrium. Two hydrogens and X2, number 9. Two H2 gas and X2 gas and 2 H2 X gas plus energy. Okay. Addition of X2 to the system here. I'm going to add some of this to an equilibrium system. Will cause what? Well, it'll cause a decrease in this one, cause an increase in that one, and it'll cause, it'll evolve some heat also. So let's see which one fits. H2 to decrease A. Yes, that's true. A is true. Got any others? Will have no effect. We'll throw that one out. Cannot possibly be carried out. I was running out of examples. H2X to decrease? No. Increase. X2 to decrease? No. Now, based upon our original amount of X2, if with the original amount would decrease, but we've added extra. So some of it we consume, but not all of it. So actually the X2 amount increases slightly. All right, so A is the only good one out of that. All right. Number 11. Which of the following statements is true? Okay. A, B, C, D, and E. When two opposing processes are proceeding at identical rates, the system is at equilibrium. Oh, yeah. That's the definition of equilibrium. Chemical equilibrium. Actually, it doesn't say chemical, it says two processes. So it could be anything. Right? We don't have none of the above statements is true. All right, so this one can't be right. We've got one that's true. Actually, we found our answer. But let's look at the others just in case I get sneaky and change them up. Catalysts are an effective means of changing the position of equilibrium. No. All catalysts do is change the rate. So the rate of the forward reaction and the rate of the reverse reaction are increased, but they still balance. The concentration C of the products equals that of the reactants and is constant. Not necessarily. We already know that you can have almost no products or almost no reactants and still have equilibrium. And then D, an endothermic reaction shifts toward reactants when heat is added to the system. Well, let's see, if we have reactants yield products, which side would an endothermic be on? Be on this side. Okay. So in that case, if we add heat, then it shifts toward products. We increase this, we get a shift toward products. So as written, that was wrong. The only one that's correct is A. All right, let's see, how about 14? Let's see, how much time do we have? Go to 10:25, okay. Consider this reaction. Sulfur dioxide plus oxygen. Okay, yields sulfur trioxide gas. Okay, is that balanced? That's 4, 5, 6, 6. Yeah. Okay. What else are we getting? For the system at equilibrium, which of the following explains what happens after the addition of oxygen gas? Assume constant temperature. So we're going to add oxygen gas. So what's going to happen? Well, sulfur dioxide is going to decrease, sulfur trioxide is going to increase, and the equilibrium shifts to the right as written. The amount of SO3 increases. That's A or E. So we could have A or E as possibilities. Now let's look at the rest of it. A increases and the value of K increases. Well, if we're gonna, well, no. K doesn't change, its temperature doesn't change, right? So A's out. E should say K stays the same. Yeah, that's it. We didn't mess with the temperature. I suspect it's exothermic. Looks like a combustion to me. 15. All right, consider the endothermic reaction. All right, 2 bromine chloride, 2 Cl, and that's a gas, is in equilibrium with that and probably this. And it's endothermic. So the heat term is on this side. All right, that's what we're given so far. Okay, what will be the effect on equilibrium of this is one condition that change the volume at constant temperature. Okay. Well, wait a minute. Changing the volume, it doesn't say which way to change the volume. Actually, it doesn't matter. Right?
Good question. Are you having lunch today?
Yeah, sure. We got 2 moles on this side. And we got 2 mole on this side. So changing the volume, no change in equilibrium. Okay. How about the second one? Increasing the temperature at constant volume. Okay. Increase temperature at constant volume. Well, increasing the temperature adds a heat on this side shifts to the right. So the equilibrium should shift toward products. But for A, there's no change in equilibrium. So let's see, let's look at our choices. No change in equilibrium is either D or E. Based upon this condition, our answer is either D or E. And then for the second one, which is actually a different experiment, equilibrium shifts toward products. So that would be D. All right. Moving on. Let's see, who do I have marked next? Here we go, number 20. The following reaction is allowed to reach equilibrium in a glass bulb at a given temperature. So we have mercury 2 oxide, solid, reaches equilibrium with mercury metal plus oxygen gas. Right? Yep. Delta H is 43.4 kilocalories per mole. And I assume that's exothermic because there's no sign given. Well, there's an implied sign. 43.4 kilocalories per mole. Okay. The mass of the HGO in the bulb could be increased by. All right, what's the expression? The equilibrium expression, that's a solid, that's a liquid. The only term in here is oxygen. That's it. So we want to increase the mass of this one. That's the effect we want to have. How would you do that? Let's see. Our choices are remove some mercury. No, that would shift this way and decrease that amount. Right. So let's see, let's put them up here. A, B, C, D. So if we remove some mercury, that won't do it. It goes the opposite direction. Reduce the volume of the bulb. If we squeeze the bulb, yeah. If we squeeze the bulb, then that stresses the system by increasing the oxygen concentration and forces it to shift to this side because there are no gases on this side. So it's a comparison of 1 mole versus no moles of gas. Okay, that's an unusual. We haven't had one of those before. So this one should work. It should shift to the left. Adding more mercury. No, adding more mercury won't change the equilibrium because it's not part of the expression. Increase the temperature. Well, if it's exothermic and we increase the temperature, well, no, it's endothermic, excuse me. Goes on this side. That won't work. Increase the temperature, go the wrong direction. Yeah. And removing some oxygen will also go the wrong direction. So none of these work. It's just B. Squeeze it. And that should get you where you want to go. It's easier, but it's smudgy. All right, 21. At 500 K. Okay, here's the governing equation. ONCl. 2 ONCl. These are all gases. And 2NO plus chlorine gas. Yeah. We have to assume that they're all gases, or did it tell us? Yeah, 1 mole of gaseous is placed in 1 liter container. So this starts off at 1 molar concentration. At equilibrium, it's 5.3% dissociated according to this equation. So at equilibrium, we've lost 5.3%. Okay, this compound. So our K expression is NO squared, chlorine, and then ONCl squared. Okay. And we want to determine the equilibrium constant. Let's see. At 500 K, I doubt that that's needed. I think that's extra information. All right, so if we set up our ice table, this is initial concentration here. 1 molar, nothing there, nothing there. Change, and then equilibrium. Okay. So we know that 5.3% of this has been dissociated, which means this is we're losing 0.053 times 1 molar. The decimal equivalent of 5.3%. Okay. So that's what we've lost here. So what does that leave us? Well, that leaves us let's see, 7, 5 minus 4. That's what we're left with. The reactant. The products then would be, this is equal amounts. So this is going to be 0.053 molar. This is going to be half of that, right? Because the ratio is 2 to 1. So what's half of 0.053? I better get my. I'm sorry? Yeah. Molar is added to each side. So at equilibrium, we have 0.053, 0.027. Now all we have to do is stick it in the equation. Right? Okay. So K is going to be, NO is 0.053 squared, and the chloride is 0.027 divided by 0.947 squared. Now let's see, 0.053 and square it. 0.027 times, and then 47 and square that. So I get 8.46 times 10 to the minus 5. And I end up with 8.3. Make a calculation error. Let's see.
I don't know, in the word form you have 8.5, but then you still have to put the A's correct. So I guess closest.
Oh, closest, yeah. Okay. So yeah, this is a review document, and I probably haven't changed it in years. So the error still sits right there. Yeah, the nearest one would be 8.3. Now, if I had none of the above, you could mark that and get credit for it. Probably have to show me your workbook. All right, next. 24. Let's see, what do we got here? Nitrogen gas reacts with hydrogen to make ammonia. Good old Haber-Bosch. Nitrogen gas reacts with hydrogen gas to make ammonia gas. All right, the balanced equation is not that. You have to balance the equation. So with 2 nitrogens here, we need 2 here, which makes 6 hydrogens, put a 3 there. Now we're balanced. At 200 degrees in a closed container. So we've got a temperature of 200 degrees Celsius. Yeah, in a closed container, 1 atmosphere of nitrogen gas, 1 atmosphere is mixed with 2 atmospheres of hydrogen gas. Okay. At equilibrium, the total pressure is 2.2 atmospheres. What's the partial pressure of hydrogen gas at equilibrium? All right, so these are the initial conditions. There's no ammonia to start with. We're going to get a change, and then at equilibrium, we're going to have a certain amount. And what we want to determine is what's the partial pressure of hydrogen. This is the one we want right here at equilibrium. Excuse me. Let's see. Total pressure at equilibrium is 2.2 atmospheres. All right, so total pressure, according to Dalton's law of partial pressure, would be the summation of the pressure of nitrogen, pressure of hydrogen left over, and the pressure of ammonia. And that's equal to 2.2 atmospheres. Okay. Okay. So we know the equilibrium is going to shift that way. So we're going to lose some of this. Actually, let's try to keep everything whole number. Right. So if we have okay, that's fine. We'll lose some of this. That means we're going to lose 3 of these. And we're going to produce 2 of those. All right. Let me see. Am I barking up the wrong tree? 1.4. Trust myself anymore. Okay. So what we have at equilibrium is 1 minus x. I think the word problem is a little bit different. It uses fractions, but this should work. And this is 2 minus 3x, and this is 2x. Okay. Oh, there we. Okay, yeah. We can put this term, and this term in here, here, and here. That gives us an equation in one unknown. Yeah, okay. So let's see, we have 2.2 is total. And this is going to be 1 minus x. And this is going to be 2 minus 3x. This is going to be 2x. There we go. So let's see, we don't have any multiply terms. We've got 1 plus 2 is 3. Right? Then we have a minus x, minus 4x, and a plus 2x is plus 2x, correct? Okay. Then we can take this on the other side. Let's see, is that right? No, minus 2x, because this is minus 4x and a 2x. There we go. Okay, now we'll bring this on the other side, which would be minus 3 plus 2.2 would be minus 0.8, correct? And x would be 0.8, because the minuses cancel, divided by 2, should be 0.4 atmospheres. Is that what we got? No. How did I get 0.8? Okay, what did I do wrong? Started off with 1 atmosphere here, 2 atmospheres here, nothing there. And we're going to lose 1 of these and lose 3 of those and make 2 of these. So that's 2x. This is 2 minus 3x. This is 1 minus x. So 1 minus x, 2 minus 3x, 2x. It's 2.2. Maybe I made a mistake here. This is 1 and 2 is 3. This is minus x minus 3x plus 2x. It's minus 2x. Three minus 2x. 2.2. Okay. That 8. Yeah, it's 8. I get 0.4 atmospheres. Wait a minute. Calculate the partial pressure of hydrogen gas. Oh. Big dummy. That's X. You saw that, didn't you? We're going to tell me. So 0.4 goes in right here. So that's 1.2, and this is 2.0, and that's 8, 0.8. Here we go. Sometimes when you overthink the problem. And notice, oh, good. Well, none of these. If I didn't catch that mistake on an exam, I'd have put none of these. Now, what I should do is put 0.4 in there as an answer. Let's clean it up better than that. All right. Next, 25. Oh, we're at it again. Haber-Bosch. Right, let's try this one. So we have 3 hydrogens and a nitrogen. 3 hydrogens plus a nitrogen. These are all gases. Equilibrium with ammonia. Okay. Equilibrium concentration of ammonia is 0.55 molar. That's this. Initial change equilibrium. So this should be 0.55 molar at equilibrium. Go. The value for K at 700 for the formation of ammonia is, okay. K is going to be ammonia squared over hydrogen, the third, and nitrogen to the first one. We just need values. All right, how did it get here? We're starting off with 2 moles of nitrogen and 4 moles of hydrogen. This is 2 molar because it's in a 1 liter container. And 4. There we go. That works better. So we are going to get some product over here. And how did we get to this point? Well, if this is 0 and we got to that, then the ratio from this to this is for every one of these, you get 2 of those. So this must be half of that. Right? And this should be, let's see, 2/3. Right, 2 to 3. This should be 2/3 of that. 0.55 subtracted from those 2. Right? If we have 0.55, let me just check myself, of ammonia, and we want to convert that to hydrogen. And hydrogen's 3, ammonia's 2. No, it's 3 halves. Good thing I checked myself. 3 halves of that value. Okay? All right. And that's subtracted from 4. So let's take 0.55, 3 times 2 divided is 0.825. 0.825 subtracted from 4 is 3.175. And half of 0.55. Yeah. About 0.55. It is. Well, this is 0.275 subtracted from 2 is 1.725. Now we have all of our terms. We just plug them in. Ammonia, 0.55 squared. Hydrogen, 3.175 cubed, and 1.725 for nitrogen. See, switch this one. Okay, if I did this right. 5.5 times 10 to the minus 3. Yeah. I divided where I should have multiplied when I should have divided. So I just inverted my answer, and that's what I got. Great, my own mistake on the fly. Okay. Stop me if you have questions. Really just a matter of working a lot of these things. Okay. 26. Okay. We're given the equilibrium constants for these two component equations, K1 and K2, and we want to put them together to make the target equation of 2 coppers plus oxygen yields to copper 2 oxides. Okay. All right, so I want to start, I like to work backwards. Let me put the component equation on top. 2 coppers plus oxygen yields 2 copper 2 oxides. Okay, and we want the first one has copper on the left-hand side, which is where it should be. So if I write it as given, we've got too much copper. And we get copper 1 oxide as a product. But the K for this is K1. All right, we only need half of that. So we got to divide by 2. Okay, which means we have to take the square root of that one. Right, this becomes the power of the K to give us our new K. So now our K is K1 to the 1/2. Okay, that gives us 2 here, 1/2 there, and 1 there. Okay, now the second one has copper oxide on the left-hand side, and we want it on the right-hand side. So I'm going to go ahead and write it on the right-hand side, which means that we have to invert the K2. Right. If we flip the equation, then the K is inverted. So if we have 2 copper oxide on this side now, with that second equation, and put side here And plus a half oxygen there. And now we have K2 to the -1. Inverted. All right. So does it work? Okay, this one, there's one of those and one of these, they cancel. There's one copper. We have a half and a half. That's good. And we have two here. That's good. Okay, so when we add this together, we get that equation. So what do we do with these? Well, to get the equilibrium constant, when you combine equations, you multiply the constants. So we're going to have K to the 1/2 times K2 to the -1. Okay, which means that this is in the denominator. So actually, it's probably going to be written this way, divided by K2. Let's see. E. E looks like the best answer. Okay. All right. That's 26. Let's see. I'm not talking about 26 anymore, are we? No, we're on to something new. All right, 28. Exactly 1 mole of dinitrogen tetroxide is placed in an empty 1 liter container and allowed to reach equilibrium by this equation. Okay, so the controlling equation is dinitrogen tetroxide is now in equilibrium with 2 nitrogen dioxide gas. Okay. What's the value of the equilibrium constant? Okay. We're given, let's see, initial change equilibrium. Let's see how that fits. And we're given we're not given the constant. So it's going to look like this. NO2 squared over N2O4. Okay. We are told that 37% dissociated. So whatever we start with, which was 1 molar and nothing here, we lost 37% of this. So if we lost that much, 37% of 1 is 0.37. So that means we have left over 6.3 molar, correct? That means if we lost this much from here, that means we added twice that much over here, which is 0.74 molar. Okay. So now all we have to do is put these values in. This is going to be 0.74 squared over 0.63. That should give us our answer. 0.74 squared and 0.63 divided. So I get 0.87. E. Nine o'clock. Okay, we're good. Check my emails. That's Madison. Did Madison send me a message? Okay. Carrying on. Number 29. All right, this reaction, hydrogen and iodine. Yields to hydrogen iodides. And the K is 44.8 at a high temperature. K equals 44.8. Okay, the importance of the high temperature is that means all of these are gases. Otherwise, if you think these are standard temperature and pressure, you're going to say iodine is solid and it's not part of the reaction. But at a high temperature, these are all gases. That's an important detail that could get lost in the question. Equimolar mixtures of reactants give the concentration of the product to be 0.5 molar at equilibrium. So equimolar mixtures of the reactants at initial conditions, we have the same number of moles or molarity for each one of these. And equilibrium. Concentration of the product is 0.5 molar. 0.5 molar. So how did it get there? Well, we had to add this much. Right? There had to be that much added to it. Where did it come from? Well, it came from here. Right? Well, if this represents 2, then each one of these has to be 0.25. Okay? All right. Which means that this expression is x minus 0.25, and this is x minus 0.25. Right? So the question is, determine the concentration of hydrogen at equilibrium. That would be this one, this expression right here. So 44.8 equals hydrogen iodide squared over hydrogen and iodide. Okay. We know this concentration here is 0.5. We know these two are x. Well, they're the same terms, minus 0.25. So this one is also squared. Correct? Or did I jump too quick? What does that mean? Well, in mathematical terms, if we square this one and square that one, that's the same thing as saying 0.50 divided by x minus 0.25, square the whole thing. Okay? So, if we take the square root of both sides, square root, do better than that. Square root of 44.8 equals 0.50 over x minus 0.25. All right? Okay. So let's take the square root of 44.8, which is 6.693. And then, yeah, let me go ahead and write it out. Over x minus 0.25. Okay. If we move this one in the denominator over here and put that one in its place, we get x minus 0.025 equals 0.5 minus, divided by, 6.693. 0.5. And this is 7.5 times 10 to the minus 2. we don't have to solve for X because the answer we want is this X minus 0.25. So this is our value right here, 7.5 times 10 to the minus 2. Okay. Right. Nine, 30, excuse me, 30. Okay, we've got 2 hydrogen fluorides. Oops. What possessed me to do that? Yes, is in equilibrium with hydrogen and fluorine gas. And the K is 1 times 10 to the minus 2. Okay. Let's see, we're looking for. Oh, just determine the reaction Q. If we have 1 mole of HF, 0.362 moles of H2, and 0.75 moles of F2 in a 5-liter flask. So we've got 1 in a 5-liter flask. And we've got 0.362 hydrogen in that same 5-liter flask. Liters, moles, and fluorine is 0.75 in a 5-liter flask. Calculate the Q. All right. Well, that's simple enough. Q then would be the non-equilibrium concentration of H2 to the first power and fluorine to the first power divided by HF to the second power. So what we need is 0.362 per 5 times 0.750 per 5 divided by 1 per 5 squared. Okay. All right. I'm going to try to simplify this without using my calculator. If we multiply these two together, that's this one times this one and that one squared. This one is also squared. That's in the denominator of the numerator. This is in the denominator of the denominator. So they're cancelable. So this one cancels out. And now we have is 1 squared. So what we really have is 0.362 times 0.750. That should give us our answer. I get 0.272 is the Q. That's B. Okay. While we're here, which way is this thing going to move? Well, this is 1 times 10 to the minus 2, which is 0.010. That's much bigger than this value. So that means we've got too much product. It's going to move back toward the reactants. Okay. consider this equilibrium number 31. Two nitrogen dioxides is in equilibrium with what? Nitrogen, one oxide and oxygen. Okay. The Kp is 0.604. Find the equilibrium pressure of O2 gas if N2 gas pressure is 0.52 atmospheres and NO is 0.3 at equilibrium. Okay. So we can still set up our ice table. But we're going to be working in pressures because of the Kp expression. All right. 0.52 atmospheres for NO2. 0.52 atmospheres. At equilibrium, yeah. And NO is 0.3. Oh. That's simpler than I expected. So 0.604 is going to be equal to the partial pressure of NO squared times O2, partial pressure of O2, divided by the partial pressure of NO2 squared. And this is our unknown. And we want to find out what this one is right here. So, NO is 0.300 squared. And this is our unknown. And this one is 0.52 squared. Okay. Okay, I think it's simplest just to go ahead and crunch the numbers. 0.3 squared and 0.52 squared, divide those. So this is 0.3328x equals 0.604. So x is going to be 0.604 divided by 0.3328. I get 1.8. Got 1.8. That's C. Okay. All right, 32. Carbon disulfide and chlorine react to form disulfur dichloride and carbon tetrachloride. Okay, so we got carbon disulfide gas reacts with 3 chlorines to produce disulfur dichloride gas and carbon tetrachloride gas. Okay. 2.14 moles of carbon disulfide and 5.85 moles of chlorine are placed in a 2-liter container, allowed to come to equilibrium. So we got our initial conditions are 2.14 mole per 2 liter. And 5.85 mole per 2 liters. And nothing there. Are found to contain 0.62 moles of carbon tetrachloride, 0.62 moles still per 2 liters. Remember, equilibrium is based on concentration. How many moles of chlorine are present at equilibrium? All right. So in order to get to this value, maybe I better calculate those values first. 2.14 divided by 2. I should be able to do that with my head. This is 1.07 molar. And 5.85 divided by 2 is 2.925. There we go. And this one is 0.3. Okay. So how did it get here? Well, we had to add 0.310 mole. That means we had to lose the same amount on this side because it's 1-to-1 coefficients. But we also had to lose 3 times that amount to get there, minus 0.930 molar. Okay. Let's see. We probably, we don't need to do the equilibrium calculation because we know how much was lost from here. So really what we've got is 2.925 to minus 0.93. So we have 1.995 molar. What was the question? How many moles of chlorine are present? This is the concentration in 2 liters. So remember, molarity equals moles per volume. So molarity times volume equals the number of moles. That means we have to multiply this times 2 liters. And that's equal to 3.99 moles, which is A. I didn't let that one catch me. All right. 33. Well, we're doing several in sequence here. 33. At minus 80 C, the K for the reaction N2O4 2NO2 is 4.6 times 10 to the minus 8. A equals 66 times 10 to the minus 8 for this reaction. Oh, and the temperature, just put that up here for laughs. There we go. N2O4. NO2 gas. We introduced 0.47 moles of N2O4 into a 1 liter vessel and let equilibrium be established. The total pressure in the system at equilibrium will be. Okay. So we start off with 0.047 moles in 1 liter. 0.047 moles in 1 liter is that molar. And this is 0. So we're going to lose some of this, and we're going to add twice that much because of the coefficients. So this is 0.047 minus X, and this is 2X. What we want to know, the total pressure in the system at equilibrium. So actually, the volume is 1 liter. Temperature is that. We need to know how many moles total in order to determine the final pressure, because we're going to have to use the ideal gas equation. Okay, so this expression 4.66 times 10 to the minus 8 equals NO2 squared over N2O4. All right, so NO2 is going to be 2X squared over 0.047 minus X. Okay, that's going to give us a quadratic. So when you have a K this small, you can say that the loss of X is going to be very little. It's not going to take much of that compared to this value. So what we can do is approximate this to be 4X squared on top over 0.047 on the bottom. And X is insignificant compared to this value. Okay. So now 4X squared is equal to 0.047 times that value. Which is 2.1902 times 10 to the minus 9. And that means X squared equals that value divided by 4, which is 5.476. 10 to the minus 10, and X equals the square root of that value. 2.34 times 10 to the minus 5th molar. Okay, so we were correct, and we could do the 5% calculation, but I'm pretty sure 10 to the minus 5th is a whole lot smaller than 10 to the minus 2. Excuse me. So when we subtract this from this, we're essentially going to get that value. I mean, we can go ahead and do the calculation. All right, subtract this one here from that value. Let's see. 0.047, and then subtract that. 4.698 times 10 to the minus 2. And this value is going to be 2 times that value, which is 4.68 times 10 to the minus 5 molar. Okay, this is molar. How many moles? What's the size of the vessel? 1 liter. So 1 times that, it's moles. Each one of these is moles. Okay, so the total moles is that value plus this value. Which is total moles equals 7.02 times 10 to the minus 5 moles. All right, so PV equals nRT. We want to find pressure. Pressure equals nRT over V. And the number of moles is 7.02 times 10 to the minus 5. Oops. And R is 0.0. Oops. Get together, Dave. 8206. And then times temperature, which is minus 80 plus 273. and divide that by volume, which is 1 liter. All right. So I've already got this one in here. I'm gonna multiply it times 0.08206. Times. Yep. And then 273 minus 80. Times. And I get 1.11 times 10 to the minus 3 atmospheres. Okay, what did I do wrong? Is everything okay up to here?
I mean, you got the right numbers, didn't you?
Huh? 33. Okay. Okay, X is this value. Okay, that's good. Total moles. 0.047. Okay. Maybe I put them in wrong. And oh. Yeah, 0.047. Where did I get that? Okay, this is so much smaller than that one. Actually, the number of moles is 0.047. So that needs to go right here. And that should give us 0.31, right?
0.74.
Oh, 74. Atmospheres. Okay. Oh, now I got that other number.
I think you multiply this with dividing.
Yeah, yeah. All right. $34. Sample of solid ammonium nitrate placed in an evacuated container, heated so it decomposed. Okay. At the equilibrium, the total pressure in the container was 2.63 atmospheres at 500 degrees. Calculate the Kp and the Kc. Okay, let's see. Ammonium nitrate. Solid. Decomposes to N2O gas plus water vapor. All right. Total pressure in the container at equilibrium is 2.63 atmospheres. All right, so it's only going to be dependent upon these two gases. 2.63 atmospheres is equal to the pressure of N2O plus the pressure of H2O. And the expression, equilibrium expression for Kp, since this is a solid, we're only going to have the numerator, right? The pressure of N2O times the pressure of H2O squared. All right. Let's see. So we're gonna end up with something here. The pressure of H2O here. Pressure of N2O here. This. This has to be, let's see, if this is X, this has to be 2X. Right? And if we start off with 0, then this is our X and this is our 2X. And X plus 2X is equal to 2.63. Okay, there we go. So this is actually 3X. And X equals 2.63 divided by 3. Zero 0.877 atmospheres. So this is 0.877. And this one is twice that. 1.75. Oh, okay. Now we got it. So the KP is going to be 0.877 and then 1.753 squared. Let's see, square that one and then 7 times that one, I get 2.696 is KP. All right. Yeah, 2.7. Okay, in order to calculate the other one, we need the converter, which in useful information should be here. Right? Hope it's here. No. I don't see it. You? Ah, there it is. K equals KC RT changing in. RT to the delta N. Okay, so what's the change in moles? Well, final minus initial. Final is 3, right? 3 moles minus 0 equals 3. So this number right here is equal to 3. This one, I think is the 0.08206. So we get 2.696 equals, that's our unknown. And then this is 0.08206 times temperature, which is 500 plus 273. And that's to the 3rd power. Okay, so we can calculate all of this right here. So that's 63.4 to the 3rd power. There. So this is KC times 2.55 times 10 to the minus 10 to the 5th. Then KC is 2.696 divided by 2.55 times 10 to the 5th. 1.05, that's 10 to the minus 5. I don't know, is that? Did I put that one in there? No, that was something I added later. That should be right, but for some reason, it just doesn't make any sense. Because this is huge, this is small. Must have made a calculation error. Should this be the joules R? Yeah. Which is 8.3145. (773 degrees), 8.3145 times, and then cubed. Yeah, I think that's going to make it worse. Yeah. That's going to make it worse. All right. Well, I had a good idea. It just logically doesn't make any sense unless it has to do with the one is expression in molarity and the other one's partial pressure. Let me look at something. Hold on a second. That's right. Yeah, that's correct. Okay, 36. Okay, yeah, we're doing okay. At a certain temperature K for the reaction 2NO2 equals N2O4. So we reversed that former equation now. N2O4, those are both gases, is 7.5. At a certain temperature, K is 7.5. And this is in molarity. If 2 moles of NO2 are placed in a 2-liter container, 2 moles of NO2 in a 2-liter is 1.0 molar. Excuse me. Oh, only one. I'm permitted to react at this temperature. Calculate the concentration of N2O4 at equilibrium. Okay, so if that's 0, that means we're going to lose. We're going to add X over here. That means we lose 2X over here. Okay, so we're going to have X here and 1 minus 2X here. Excuse me. And K 7.5 equals N2O4 X over 1.0 minus 2X squared. Now, this K is so large, right, which means it's really far to that direction. That K is a significant fraction of 1. We cannot estimate that one. We have to take the quadratic, right? So let's expand this quadratic. X over 2X squared minus 2X squared is 4X squared. And then 1.0 that term. And then the x term is minus 2x times minus 2x. Let's see, minus 2x plus minus 2x is minus 4x, correct? Okay. Excuse me. So 7.5 times this expression. 7.5. 4 times is 30. X squared minus another 30. X and then plus 7.5 equals X. So now we have to get all our terms on one side and equal to 0 in order to use the quadratic. Excuse me. This becomes a minus on this side, so it's 30 x squared minus 31 x plus 7.5 equals 0. So I got my quadratic on the back here. So x, put it over here. X is going to be equal to this term, a minus 31. Let me put it up there like that. Minus 31 is b plus or minus square root of b squared. So it's minus 31 squared minus 4. A is 30 and C is 7.5. Okay, and this is all over 2 times A, which is 30. Okay, so X, let's do the plus first. Actually, let's do everything inside here. So 31 squared is 961. And then we subtract 4 enter 30 times 7.5 times. We subtract 900. Nice. And then take the square root, which is 7.81. That's this term right here. So this is going to be a plus 31, right? Minus times a minus. This is going to be 60. So X is either this one plus that one divided by 60, which is 0.647, or 31 minus 7.81 divided by 60, which is 0.370. Okay, which one makes sense? Well, 2 times x, 2 times 6 is 1.2. Can't be. You can't subtract that much from this much, right? So that one's out. It has to be 0.370. Now, what was the question? Calculate the concentration of N2O4. It's X. Okay, so we found it. Well, nearest one. You could say none of these, really. Unless I made an error in calculation. Okay. Excuse me. Oh, that's it.